Okay, so currently we are learning about the instruction set, right? Last time we looked at the simple arithmetic instruction, which is add instruction and addi instruction. So, and also at the last time we look at the memory operation. So let's look at this memory operation. Okay, so memory operation, memory operand here. Okay, so memory. So for the arithmetic operation, every data should be in the register, right? So the arithmetic operation case, we cannot access the memory value directly. In order to access the memory, we need to use some special instruction, which is load instruction and store instruction. And load instruction is loading value from memory to the register, from memory to the register. And store instruction is storing the result from register to memory. Okay. And then to access the memory, we have to give address. In the MIPS case, the address is byte address. Okay, so byte address. So which means that each address, 1 byte is corresponded. Okay, so for instance, address is 0, then we can access 1 byte. Okay, so and address is 1, then is returning another byte. So for each byte, one index, one address is attached. So currently we are using the 32-bit machine, right? 32-bit machine. That means the address size also 32-bit. Okay. So using 32-bit, how many items we can distinguish? So using the 32-bit, we can distinguish 2 to the 32 cases. Is it right? Everything is 0, 0, 0, 1, 0, 0, 1, 0, da, 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 1, 1, everything is 1. So this is 32-bit. Then there are 2 case, 2 case, and 2 case. So there are 32 twos, right? Which means that 2 to the 32. So for there are 2 to the 32 addresses. Okay, for each address, 1 byte is mapped. Okay, what's the 2 to the 32 value? Which is 2 to the 30 by 2 to the 2, right? 2 to the 10 is 1K kilo. 2 to the 20 is 1 mega. And 2 to the 30 is 1 giga. Okay, because 2 to the 10 is 1024. So we are saying that this is 1000. So it's 1K. 2 to the 20 is 1 mega. 2 to the 30 is 1 gig. So 2 to the 32 is 4 gig. 4 giga. And so there are 4 giga addresses. For each address, 1 byte is mapped, so that using 32-bit address, we can access 4 gigabyte memory. Okay, because for each address, 1 byte is mapped. Okay, so 4 gigabyte is the maximum address size, maximum memory size to access using 32-bit machine. So anyway, each address is identifying 8-bit byte, 8-bit byte, so 1 byte. Okay, And then word. Word is a basic unit to transfer between memory and register. Okay. So register size. What's the register size? Do you remember? Register size. So in MIPS, how many registers are there? From 0 to, do you remember? Yeah, 31. So there are 32 registers. And each register size is also 32-bit. Okay. 32-bit is how many bytes? 4 byte. Okay. So this 32-bit is, or 4 byte is called one word. Okay. So the basic transferring unit between register and memory is word size, because register is one word. Okay. So the words are aligned. So word is 4 byte, right? So to read one word, the address should be multiple of 4. So what does it mean is, here there is a register in the processor, which is 4 byte. Okay. In memory, there is address 0, 1, 2, 3, 4, 5, 6, 7, 8, right? Okay. And register is divided into the 4 byte. Okay. So if we are giving address 0, then it is returning 1 byte, right? This 1 byte is mapped onto the first location of the register. Address is 1 in the case, the second byte. So second byte is moved to the second location of the register. Okay. And address 2, and that's the third byte. And finally, last one. Okay, address 3. So to fill the register, we have to read 4 byte, right? So 4 byte. So instead of moving 1 byte from memory to the register, the instruction of load instruction case, it is actually load 1 word. Okay, 1 word. So that instruction is actually LW, 1 word, load word. So in this instruction, load word, LW instruction case, if this is giving one address, like address 0, then instead of loading single byte, it is returning 4 byte. Okay, so 4 byte, this much is loaded, and then this is actually stored into the register. Okay, so load word instruction case, we have to give address 0, then is returning 4 byte, which is 1 word, and 1 word is filled into the register. Then what about the next address in this case? To read another word, the next word is starting from the 4, right? Then we can read 4 byte. And next one, 8, right? From 8. This is another word. So load word case, the address should be multiple of 4. Okay. So the address should be 0, 4, 8, 12. That is only possible. So like address 1, this is not allowed in the load word case. Okay, because load word should be loading one word, which is 4 byte at once. So it should be aligned. Okay. So address must be multiple 4. And last one, MIPS is big Indian. So big Indian means, what the big Indian means is, it's a very simple thing. So there is a register and there is a memory. So memory has address 0, 1, 2, 3, and each one is mapped to this register, right? So in the register, this is a high position. This is most significant bit. Most significant bit. And the last one is LSB, least significant bit. Okay. So if the 0 location is moving to the highest position, as 1 is moving to the next location, 2 is moving to the next one, and 3 is moving to the last one. So 0, 1, 2, 3. So the byte is located like this. This is called big Indian. Okay. It's just like an array move, big Indian. So for instance, in your C code, maybe you learn about the like this one. There are 4 byte character. C is 4. And there's integer I. And sometimes maybe you are making the union. In C code, union. Union means it is sharing, right? Character and integer is shared. So this 4 byte sometimes is used as character, or sometimes it can be used as an integer. So C4 case, this is the C0, C1, C2, C3. So C0 is representing the most significant bit or higher bit. Then this representation is big Indian representation. Okay, so MIPS is following this big Indian approach, and also ARM is also following that representation. So then there may be another one, right? So there is Little Indian also. Maybe you can guess what's the Little Indian. Little Indian case is opposite. So there are 4 byte register, and there is a memory, and memory 0, 1, 2, 3. Then the location of 0 is placed in the last one, and 1 is here, 2 is there, and 3 is here. Okay, so this is 3, 2, 1, 0. So the location is opposite. So that is called the Little India. So Intel processor, Intel x86. So Intel processor is using this Little Indian approach. So when you are looking at the memory structure, then Intel and ARM or MIPS are different. Okay, so anyway, we will use this big Indian approach. Okay. Then let's look at the example of memory. Operand. Okay, so this is C code. C code. So this is doing variable G, variable H, and is accessing the array A, right? So array case, what is happening is A is representing the starting address of the array. So A means it is equal to the A0 address. Okay, is the same to that. Okay, so this meaning is, this instruction meaning is we have to read data from H, and then we have to read data from this array. Okay, so this array means there is a memory, right? Memory is here. So for instance, A is 1000, for instance, so 1000. Here, array A is stored, okay? So A0 value is stored here. And then let's assume that this is integer type. Where is A1 array location? What's the address of that? 1004, right? So it should be increased by 4. And A2 is starting from 1008. Then what's the 8? What's the address of that? 1000 plus 4 times 8, right? So yeah, this is 1032. Okay, so that's the address of that. Okay, so for instance, let's assume that register 1 is containing A's value, which is 1000. Okay, then how can you compute address of 8? It should be, we have to add $1 plus 32, right? So this is address actually. This is address. So which means that we have to give load word instruction, and address is based on the $1 and then 32, which means $1's value plus 32. And the result, the value should be stored into some another register. Okay, so this is the meaning of that. Okay. So then let's try to do the exercise. So we'll try to exercise load $2, 32, $1. Okay. So before that, let's give some value here. Okay. So we just give a 0 value to the $1. So maybe we don't need it, but anyway. And then if we are running this code, then maybe there's nothing. So initially the memory will be 0 value or garbage value. So the garbage is loaded. Okay. So can you go to the simulator? So go to the simulator. Okay. Then let's try to look at that instruction again. Addi 0, 32. Let's try to do that. So can you run it by yourself? So if you are completed, please let me know using the chat window. So if you are running it, and that. So nothing is changed in the restart one. And then we have to look at the memory, right? So memory location is 0. So here we are giving 0. So nothing. That. Nothing is changed. So before the loading, let's try to store something. A lot 3, 0, 7. And then store $3, 2, then run that one. 0, this is 7, and store into the 32. So there is a 32 place here, right? Here is a stored, and then load that value into the file. So can you do it? So everyone can use the simulator. So the website is I already posted on the chatting window. So everyone completed, or do you need more time? Okay, so someone is asking me that 7. Why 7 is stored at that location? That's is your question. Is it correct? Okay. So here, store is performed by the store instruction. Okay, store instruction. $3 is already set by 7. Okay, and the line 2. So $3 is 7. And store instruction is just storing this $3 value into the memory location. Okay, so this is representing the address of memory. Okay, so address of memory 32 plus $1. $1 is 0, right? So address is 32. Okay, so let's look at the memory. This is memory location 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? Okay, so there are 12 address. So there's 24, and the starting point is here. This is actually 32. Okay, so this is 32 location. 32, 33, 34, 35. Okay, so this is starting point. This is 32. At the location, what value is stored? Load word, right? A store word. Store word is storing the 4 byte. 4 byte. So which means that R3 is 00000007. This is 4 byte, right? This 4 byte is storing from this 32 location here. So 00 is stored and 000007. These 4 bytes are stored from this location. Okay. Okay, so then can you store the data onto the 1032 location and then load the value? Can you do it? So store 7 into address 1032. Can you do it? So if you do that, if you can do it, can you upload your code into the chat window? So there are so many ways. One of that is base address $1. So let's assign 1000 here. And $3 is 7. We don't need the right direction. So here address is 1032. Right? So store and step. So address, this is hexadecimal value. Decimal wise is 1000. 1000 plus 7. So this is 7. And address is 1000 plus 32. So let's look at that location. So everything is 0. And step. So then here, 000007 is stored. Okay. Then can you do this one? After storing the 1032, so A0 at address. Okay. Then A storing 5, and then to the 8, 9 is 8, 8 after loading, and then storing. So can you write the code for that one? Okay. So if you can succeed, then please post your code in the chat window. So if it's so much difficult, please let me know. So everyone finished? Not yet? Okay, so let's look at the code. So first, A0 starting address 1000. So let us assume that $1 is representing address of A0. So we are assigning 1000. And then 8 should be 5. So let's store 5 into the 3. And then we are storing that value. So $3 is stored into the 8 is 4 times 8 is 32. So this is address of 8, right? So we are storing that value. Okay. And then load 8 is value from the memory. So actually it is not required, right? Because $3 is already contained the value. But anyway, we are storing from loading from memory. And then we are doing addi. $2. We are storing some equals $2, 4, and then that result should be stored in the another register. $4. And then we are storing the result $4 into the memory. Where's the address of 89? We have to add 36. Okay. So this is the code. So I posted in the chat window. So let's try whether it's running. Step. Assemble the load first. Then step. Okay. Steps R3 is 5. And then when you're looking at the memory is changed to 5, right? 0, 0, 0, 0, 5. And load. So R2 raised to 2 is 5. And then add $2 plus 4, which will be 9. So raised to 4 will be 9. And then throwing the 9 onto the location. So can you guess where is the memory is changing? So this will be changed to the 0, 0, 0, 0, 9, 0, 9. So that's the our expectation. Okay. Okay, so then let's go back to the code again. Okay, so then can you do it? This is 3, and this is 3, and this is 5, and this is 6. So can you write the code? So if you're completing, post your code in the chat window. Okay, 4 students completed it. 5. So can you follow? Okay, so here this case, as you can see that A3 is 6. So $3 will be 6. And address will be 1000 plus 12, right? 3 times 4. And then it's loaded, added by 3, and stored into the 5 times 4 is 20. Okay. That's the result. Deep learning. Okay, that's 6. Stored into the 6. Then load. Oh. So this should be okay, 6. Then add 3 times is 9. Okay. Then store into the 9. So that's the how array and memory access is. Okay, so that's the load store instruction. Any question about the load store instruction? So maybe this is first time to learn about the memory, right? So how memory is accessed. So maybe this is not gonna be convenient or familiar to you, but through this class, I think memory access is just like a array access in SQL. Is exactly the same thing. Okay. So let's compare the register and memory. So definitely register much faster. It's much faster to the memory. So that's the reason why memory access instructions are separately implemented. Okay. To access the main memory, we need load instruction and store instruction. Okay. So to load something from the memory and then to the operation, we need the memory operation and then arithmetic operations. So it takes more time. So the compiler is translating from high-level language like a C code to the machine language. In that case, compiler is trying to minimize the memory access. So if it's possible, or as much as possible, compiler is generating the register operations without generating the memory operation. So compiler is using register as much as possible. But the number of registers are limited. So in this case, there are only 32 registers. So if we are using the many variables, in that case, we need memory. Okay, so in that case, compiler is spilling the register value to the memory. So register optimization is actually compiler's work. Okay, so immediately we already look at it at I instruction, right? The I instruction format is, so this is destination, and this is source, and this is constant value. Or we are saying that this is immediate. So add I is, we didn't know about this notation, but anyway, just ignoring about, we will learn about it later. $3 is $3 plus 4. So what about this case? Subtraction, $3 minus $3 equal $3 minus 2. So in this case, maybe you are thinking that what about the subtraction I, right? Sub I. Maybe you can think about it, but actually there is no this instruction. Sub I is not existing. Instead of that, you have to use add I. Add I support negative value. Okay, so this meaning is $3 is $3 plus -2, which is subtraction. Okay, so last one is negative. Then we can do the subtraction. So add I case, add I is existing, but sub I is not existing. Okay. So immediate operand. So later we will learn about why immediate operand is very useful to represent the constant value. So if we don't have add I, then every constant should be from the main memory, right? Memory has the constant value, and then the memory value should be loaded from the main memory to the register. So it takes more time because we have to access the memory. But add I case, the constant is already in the instruction, so we don't need to access the main memory. So it's much faster. Okay, so constant 0. So 0 value is used a lot frequently. So MIPS is dedicating register 0 as 0 value. So we already mentioned that there are 32 registers, right? So register 0, register 1, register 31. So among these 32 registers, the first register is dedicated to the 0 value. It's constant value. So $0 register, so 0 register is not going to be changing to another value. So $0 is always containing 0 value. So hardware-wise, it is not writable. In the simulator, you can change it, but anyway, in the hardware case, $0 is not going to be writable. Okay, so the register 0 is 0, so it's very useful. For instance, if you want to move from register 2 to the register 3, you want to move it. In that case, there is no move instruction. Okay, the MIPS, there is no move. Instead of that, you can use add instruction. Add $3, $2, $0. So $0 is containing 0. So $2 plus 0 is $2. Okay, so this is way, or another way is add I, $3, $2, 0. That is also possible. Okay, so there are so many ways. So to implement move. Okay. Before the sign variable, let's look at some another instruction. We'll come back for this sign variable signing thing. So we learn about some another instructions. We learn about the currently we learn about the 3 instructions. Add 4 instruction. Add I, load word, store word. Right. So we learn about this 4 instruction. Actually, there is another one, subtraction. See there, even though we didn't know about that. So let's look at the shift logically left. Shift operation. Shift left logically. Okay, so in C code, you know that X2. What does it mean? What this operation is doing? This is, what is this? It is, yeah, left shift. How much? What bit shift? 2 bit, right? 2 bit shift, right? Similarly, this is doing that one. So this is in MIPS things, shift left logically. So this is destination and source register and constant. So this is destination, source, and this is constant, 2-bit in this case. So their meaning is $3 will be containing $2 left shift. It's exactly the same thing. Okay, so that's the shift to left logically. So then definitely there is a shift right logically also. So this is exactly same thing. And 3 is 2, and not 1, 2. Okay, so there is a left shift and a right shift. So here, maybe this is not going to be familiar to you logically, right? Logically. Actually, there is another one, arithmetically shift. So we will look at it later. Okay, so just think about that there is 2 instruction, shift left logically, shift right logically. Okay. Okay, then let's look at the exercise. So we did E1 and E2 last time, right? E1 and E2. So this is using addi. This is addi. And this for this one, we use add. This is addi. And the last addi. Okay. So can you do the exercise 3? So first, $1 value will be 1. We should be assigning it. And then we have to do left, shift to left logically. So here. So can you write the code? And then can you put the result on the chat window? So instead of when you're posting the result on the chat window, please post to everybody. Send to everybody. And please write down the in hexadecimal representation. Okay. So everyone can do that, right? So based on that, so let's look at the exercise 4. So can you do it? So even though this is a single representation, but you need 2 instructions to do that, just like exercise 3. So here $1 will be 0x10000, $2 will be 11, and 11 should be stored into the 0x10000 address location. So can you write the code and then post your code in the chat window? Okay, so let's look at the real code. So here, so everyone is writing down addi $1, 0, 1. So 1 is assigned to the $1 and shift left logically by 28-bit. Source register is 1 and destination is also 1. Addi, so 11 is assigned to the $2 and then store word $2 is stored into the $1, so that's location. Okay, so let's run it. And you can see that. So first was 1, after shift, it will be 1, 0, 0, 0. $2 will be B in hexadecimal, B. And store, we have to store here, right? So this is location. And everything contains 0. After storing, it will be 0, 0, 0, 0, 0, B is stored. Okay. Okay, so then let's look at the exercise 5. So what you have to do is first, can you store value 4 and 5 into the address 10000 location and 1004 location. So actually this is 28. So can you store 4 and 5 on address 1000 and 1004? So using the E4 you can do it, right? So write your code and post it on the chat window. Yes, you just need to the first line. So store 4 and 5 on address 1000 and 1004. Storing only. So after you are writing this code, then following this code, you don't need this one because it's already there in the previous one. So can you write the following this code also? So write the whole code with this one. maybe it's okay whether it's depending on. So if you don't have this one, just include it. If you already did, you don't need this one. So that is present the. Okay. So the last should be look at the direction. So this meaning is store. And this meaning is loading. And from the memory. So the upper one will be from the memory, and last one will be from the register to the memory. Okay, then let's look at the code. So here is the code E5. As you mentioned that the first line is storing the 4 and 5, right? So 4 and 5 are stored into the 0 and 1004. And then this is loading from the location and then the subtraction and storing it. Okay. So if you're loading it, then first is 1 shift 4 and storing 4 and 5 and 5 is stored and load into the R2 3 5 is loaded and then subtraction. So we didn't know about what this meaning, but maybe we already know that 4 minus 5 is -1. Actually this is -1. So but we didn't know about that this signed value yet. And then store as FFFFF stored. Okay. So this is homework from E1, E2, E3, E4, E5. So you have to write Libs code and run them on simulator. And then submit the calls and screen capture of the simulator. So in your simulator, you can see that the memory is changing, right? Memory is updated and also register is updated. So submit these things in the homework. Due date will be next Monday. Due next Monday. Okay, so I will post this homework in the portal site. Okay. Okay. So if you cannot follow this one, then maybe the class will be getting more and more difficult. So you have to be following all the instructions. Okay. So that's the reason why I am giving the homework to you. Okay. So any question? No question? E5 code. Actually, in the chatting, you can see the E5 code, right? Yeah, IMS, it's portal site, right? So E5 code is already posted by everybody, so you can refer it. Okay. E5 code, you wanna see it? Okay. I am posting the code, okay? E5 and E4. You can refer. Okay, so yeah, see you on Monday. Bye.